Welcome to the COVID lectures. Actually, that's a bit misleading. Hold on. Welcome to the we had to change our teaching format because of COVID lectures. Okay, so all jokes aside, hopefully you guys are staying safe out there, but there's no rest for the weary. We have to keep mathing it out. So this is going to be our second COVID lecture for Math 1203 Applied Calculus. Last time we spoke about related rates. I want to continue that discussion and move into a next topic, but I asked you guys to actually submit to me your questions, and a few of you did, so I do want to address those before we actually move on. So what I want to do is address some questions that came up in the last lecture I posted. First, I'll then do a couple more examples on related rates and then move into a whole new topic, because pretty much last time I told you everything you needed to know about related rates. Those 6 steps are everything you need to know for this class. So I think what I would like to do is to actually go over one of the examples I did last time, just of course very quickly, a lot quicker than I did last time, and because a lot of the questions I think can be illustrated by parts of that example. So if we go back over this example, and I'll get to the questions that were submitted pretty soon. Example 3 from last time. So remember, our related rates problems all had 6 steps in which we had to do them. The first step, which people often overlook, is to read the question. The second step is to, if possible or necessary, is to draw a diagram. And we'll actually do an example later today where you'll see a situation where it wasn't necessarily needed, it wasn't necessary to actually draw a diagram, but a lot of times it is, because a lot of times the geometry of the situation is going to help us. Once you actually read, fully understand the question, not only do you understand that it's a related rates problem, and you draw a diagram, labeling it properly. Some of the questions came up from that aspect, I believe. Then the third thing you're going to do is you're going to write down what rates do I know, and what rates do I want. Right? Because remember, the point of a related rates problem was you were told about related quantities, and if quantities are related, then their rates are related, hence the name related rates. And we can get to the relationship between their rates by just differentiating the original relationship implicitly with respect to time. So usually what's going to happen is they're going to tell you, oh, these 2 things are related in this way, 2 or 3 maybe, are related in this way, and we know how fast these parts here are changing, how fast is this other part over here changing. So that's a typical related rates problem. So basically you're going to know some rates and you're going to not know others, and you're going to want to be able to figure out, I have to get something out of my pocket there, to figure out the rate that you want given the rates that you know. So you kind of list these to kind of know where you're heading, what the goal is, what you want to do. Once you have that, the 4th thing is to come up with the equation. And as you may recall, the equation is often going to be dependent on some sort of diagrammatic situation or some picture or some way of you conceptualizing the problem. So your step 2 is going to help you with the step 4 to actually set up the equation that it will apply. Once you actually have an equation, then what you're going to do is you're going to differentiate that equation. Implicitly, you're going to differentiate with respect to time, meaning anything that's not a t, once you differentiate that variable, you have to multiply by the prime of that variable. Like if it was a v, you have to multiply by dv dt. If it was an L, you have to multiply by dl dt, etc. So you're actually going to do your derivatives here. This is where the application of implicit differentiation comes in. This is how we're going to use calculus to help us solve the problem. And then 6 is pretty much to answer the question, right? Which basically means you're going to figure out what you wanted down here by plugging in your knowns and solving for the unknown. So let's just quickly run over example 3 again, because some of the questions that I was asked, I think, are nicely illustrated by example 3. So let's get to it. A 15-foot ladder is resting against a vertical wall. Suddenly and without warning, the foot of the ladder begins to slide away from the wall at a rate of 2 feet per second. At what rate is the top of the ladder sliding down the wall when the foot of the ladder is 9 feet from the wall? Okay, so that was a question. So we figured out last time that a right triangle is a nice diagram to use here. The vertical part here representing the wall, the horizontal part here representing the ground, and the hypotenuse representing, of course, the ladder that's leaning against the wall. So we decided to label this. I believe we labeled it A and B, but you could have labeled it whatever, X and Y. And we also labeled this side 15. And that's going to be importance. I'm going to get back to a question that came up with that again. Right? So we know that this is the situation. We know that the foot of the ladder is sliding away from the wall. So A is increasing. At the same time, the top of the ladder will be sliding down the wall, so B is going to be decreasing. Okay. Then, what did we know? The foot of the ladder is sliding away from the wall at 2 feet per second. So this tells us that we knew dA dt was 2, positive 2, in fact, because it's sliding away from the wall. A is getting bigger, it's increasing, and we know that when things are increasing, their rates are positive, their rates of change are positive. What do we want? Well, we wanted dB dt. How fast is it sliding down the wall at a specific point when A was equal to 9. Okay? So now we come up with the equation. Now the diagram hinted to us what equation we want to use, Pythagoras Theorem. A squared plus B squared equals 15 squared. And then we went to differentiate that with respect to time. So this is 2A dA dt plus 2B dB dt equals 0, because the derivative of 15 squared is 0. Now we wanted to actually answer the question. Of course, this here implies that if you divide both sides by 2, I could solve for the dB dt that I wanted. And this was actually minus A dA dt over B. And so at this point, we go into step 6, which says to answer the question by plugging in our values. So our dB dt was equal to minus A, which we know was 9, dA dt, which we're told is 2, and over here, we got that the answer was 12 for the B, which we figured out from using step 4. And that pretty much simplified to minus 3 over 2. And the units here were feet per second. Okay, so that was problem 6, right? So really rushing through problem 6 there in a few minutes. But that you can see at a glance. So that is the solution to problem 3, sorry. That was step 6 of problem 3. Okay, so now I went over that because some of the questions that I was getting, if you I can use this example to illustrate the answers to these questions. Let me just grab the questions right here. So, I'm not going to give a shout out to anybody because I don't know if that's allowed. People might want to ask their questions anonymously. I guess if you want me to hey, this question comes from math student _ 3142, whatever, you can let me know if it's okay to shout you out. But for now, the questions come from nameless students, from my other math 1203 students, among them. Okay, I just watched the first video. Everything went well. I was just wondering if you'll be posting solutions to the related rates problems. So, in general, I'm not going to post the solutions. I'm not going to work them out. So I'm going to do a few select problems from the handout on the board, and you'll see the solutions there. But other than that, I really expect you to try the others on your own. You should, for the most part, know that you're getting them right. Otherwise, it's kind of a red flag. If you're not sure about something, what you can do is just send me like a picture of your solutions, and I'll tell you whether you're right or wrong, or I'll tell you what step you went wrong in, or something like that. But I'm not really gonna do all the solutions, because I did way more. I put way more examples on the handout that I even wanted to do, and I never do more than all of them in class. It's just for extra practice for you guys. So that's the answer to that question. Another question from another person came in. This person asked a couple of questions. What are some tips you have for remembering to plug in the constants before deriving to find the unknowns? Now, I had written back to this person saying I'm not sure I fully understand the question. There are a couple places in which we plug in constants, so I'm not sure exactly which one of the places that this question is referring to. So I went through a whole problem, and I'll touch all the bases of where a constant might be plugged in, where this person might be confused, and hopefully I would have ended up answering the question. So there are a couple places in which constants can be plugged in. One was here. So for things that are not changing, things that don't change, since we're in step 2, we might be in a scenario where we might have to plug in some constant in our diagram. You have to just be careful to read very carefully and just notice in your picture what are the things that are changing, what's moving, what's increasing, what's decreasing. And if anything is increasing, decreasing, or moving, label that thing with letters in step 2. Anything that's not moving, label it with a constant. So in this case, the length of the ladder was not changing, so I would label that with 15. However, the distance the foot of the ladder is away from the wall is moving, as well as the height, how far, am I even pointing at the right thing? Okay. This is hard. Okay, maybe I'll go closer here. Okay, so the distance the foot of the ladder is away from the wall, that's changing, that's getting bigger in fact, and the height that the ladder is up on top of the wall is changing, it's falling in fact, and so it's getting smaller. So these two things here are labeled as variables. You need to plug in a constant for anything that's not changing. Not necessarily because it will be wrong to put a variable here, but because over here in step 5, I've seen it often happen that students get mixed up with all these extra variables that they're not given any values for, and then they just forget that, oh, technically that variable is a constant, so I don't need any values for it because the derivative is just going to wipe that part out. I've seen students forget that and mess up with that in step 5, so I highly recommend plugging in constants here whenever there's something not changing in your situation. So that's the first situation in which you'd want to make sure that you're plugging in constants. If applicable, you might not need them, but if applicable, definitely in step 2 is a situation where you're going to want to make sure you're plugging in constants. Before the problem even starts, before you even start to solve the problem, just for you conceptualizing things and setting them up, plug in constants in the diagram. Another place where plugging in constants will occur is in step 6. In equation 4, you're not supposed to be plugging any constants in at this stage. Here's where you're coming up with a general formula that's going to describe the situation. So you shouldn't be even worried about plugging in anything at this point. However, after you take the derivatives, namely after you take derivatives, so not before deriving, but after deriving, you're going to want to plug in constants for step 6. Now, at this point, there might be locations or in which you weren't given the constant. So this here represented the b from before, and we were not given any information about b. So in that scenario, what you want to do, if you need help to figure out what constants you want to plug in, this happens after you differentiate, right? You start plugging in things after step 5, right? So you're going to plug in constants in your diagram if applicable. The next time you should think of I need to plug in some constant, the next time that thought comes up is in step 6. Now, in step 6, you might end up in a situation where you have a variable that you need to plug in a constant for because the unknown that you want to solve for is this guy, but you don't know the value. in that case, you go here to the equation in step 4, solve for that variable, and come back, right? So those are the two places where you might have to plug in constants. So yeah, in an answer to that question, my laptop logged out here. Yeah, so in answer to that question, remembering where to plug in constants before deriving to find the unknowns, like I wasn't really sure where they were talking, but as I mentioned just now, you should be thinking of plugging in constants in 2 locations. Potentially in step 2, not always, if you notice that there's something not changing. And the next time you're thinking of plugging in constants is step 6, which is after you've differentiated and everything. So these are the 2 locations where you'll be plugging anything in. And the one nuance that might happen is that in step 6, you might not have all the information. You can go back to step 4 to find the information you need to come back to step 6. So that's where plugging in constants would happen. And in terms of tips to remembering them, it's just basically knowing the steps. Know that there's a 6-step process to solve these problems. Plugging in constants may occur in step 2 and step 6. The same person asked another question. If we forget the units or put the wrong ones down, would we get marked off? That's a fair question. So notice here that I put the units in. So here's the thing. I don't require in this class that you actually write the units at all, right? So if you got to this point and you just wrote -3/2, I'd be fine with that. I would give you 100% credit for that answer. So I don't even require that you write units at all. Not to say that units aren't important. One way in which units can be important is in the reading section. Units may be important here. But they're important in the sense of you should be able to read something and recognize whether or not something is telling you a length or an area or a volume. And that's pretty much the only kind of thing where you're going to need to know about units. So if you're reading a problem and it mentioned, 5 feet cubed, you know that it's telling you about an instance where the volume is 5. If it says, 5 feet, you know, it's telling you about an instance where the length of something is 5. So you might need to know about units in terms of whether if you see a squared unit or a cubed unit, you should know what it means and how to actually read into that for the problem. But other than that, I'm not really going to care about units. Units are important, and they're specifically more important to the problem-solving process in a class like physics or chemistry or things like that. In an applied calc class with the related rates, as long as you can set up the diagram properly and you know your data, really you don't have to think about units at all the whole time. It's not necessary. As for the second part of the problem, if you put the wrong units down, now that's a different thing. So if you got here and you wrote, this is feet squared per minute, right? So let's say you wrote the wrong units down. Now in that case, yeah, I'd have to take off a point for that because now you technically have the wrong answer, right? So it's kind of like I can't just ignore the fact. If you write down, I have to give you a grade based on what you write down, the information that you're communicating to me. If you communicate the wrong information, it's the wrong answer. I can't ignore it. So if you want to be safe, I would just say leave off units off your final answer. Just don't worry about it. Units are important, but not for this class and this topic. I'm not going to care. If you leave them off, you will still get full credit. If you put them down, make sure you're putting down the right ones. So that answers that question. What else? Okay, so that answers that question. Okay, so here is another question. This is actually the last one. In the video at 2150, you stated that the plus sign is important for the rates. So that means when a rate is decreasing, it would be essential to have a negative sign. So let's say the ladder is falling at a rate of 2, would the rate be -2? And yes, you are correct. Let me do some clarification, however. So yes, the idea of positive and negative sign when it comes to filling in rates are actually important. Namely, having a plus sign here is actually vitally important to you being able to solve the problem. The fact that the answer has a minus sign is actually very important to the answer to the problem, right? So, in our problem, we were told that the foot of the ladder is sliding away from the wall. You should understand that what that means is that A is getting larger or A is increasing. Increasing goes with positive, which means you need a +2. What would cause you to put a -2 here is something if the problem said, oh, someone is pushing the foot of the ladder towards the wall, right? If you push the foot of the ladder towards the wall, that will cause this to slide up, and what would happen is the dA dt would have to be negative in that case, because now your A is getting smaller. While if you do that, this will start increasing, so this should be a positive one. And so, yes, the signs are important, and it just basically means in the first section when you read, you have to understand what is increasing, what is decreasing. Is the thing I'm looking at getting bigger? Is it getting smaller? That's what you're going to use to kind of judge what signs you need, but the signs are important. Watch the signs. So for rates, the signs are definitely important. Positive for things that are getting bigger or increasing. Negative signs for things that are smaller, that are getting smaller or decreasing, as well as you should know whether or not the sign of your answer makes sense. So if we went through this problem and you got a positive answer here, you should actually recognize, I would expect you to recognize that something is wrong with that answer. Because a positive answer here would mean that B is increasing, but we know it's decreasing. So yeah, the signs are actually important. Yes. Something else I wanted to deal with, and so yeah, I had a couple questions here, which is good, means that people are watching the lectures and they're actually thinking about what was posted, so I'm very happy about that. Now, there were some questions that some of my students from my other class asked that no one asked here. But I think my 1203 classes are actually doing fine overall. Not many students. But it's understandable that some students are probably in the wake of all this concerned about their grades, how things are going to happen. If they did poorly on test 1, what are their chances of improving and what is the maximum grade they can get and so on and so forth. So in general, let me categorically say, like just in general, this applies to anybody in the class. In my mind, it's still possible for anyone to get an A, and right. So I'm not just concerned about you passing the class. You can get an A if you want. Okay, it can still happen. That being said, of course, it's going to be a lot more difficult for some people to improve towards that A than for other people. But in general, I am looking at improvements over time. To that end, when it comes to a particular assignment, like test 1 or some quiz or something, I'm not going to give makeups for a particular test or give extra credit for a particular assignment. I don't believe that sort of artificial pumping of the grades, if you might say, I don't agree with that philosophy, because I think it just kind of sets you up for bad habits in the future. I think many times in life you do your best, you try to prepare, and things don't work out the way you want them to. And life usually doesn't give you do-overs, you know what I mean? Like you could be an athlete training for the Olympics, you trained hard for 4 years, you get there and you don't get placed, right? You come 4th place or something like that. And the Olympics doesn't allow you to rerun the race again and, oh, let's have a do-over because, you know, the racer, the person who came in 4th place felt like they needed another chance, they want some extra credit. Like, life doesn't work that way, right? However, life usually does give you a way, or just by living, you have opportunities in the future to do better in the future, to make up to learn from your mistakes and make up for them in the future. And so, if you're the guy who didn't place in the Olympics, well, hopefully you're young enough that 4 years down the road, you can go back to the drawing board, figure out what went wrong, and so that for down the road in the future, you can make up for, quote unquote, your performance the first time. And so that's kind of how I look at things. So if you did bad on a particular assignment, I'm not going to totally just like, oh, let me just give everyone extra credit. Let me clear everything and so everyone's fine. Is everyone happy? I don't think that's actually good for you in the long run. And I think it actually sets up bad habits and expectations. That's just going to make life a little more disappointing for you than it has to be. But that being said, I do believe that over time students can improve, and I think this should be rewarded whenever it does happen. So if over time, as we move on to new topics, you're doing better, if on test 2, whatever that might look like, you perform better. If on the final, you perform better. And so let's say the final is going to be cumulative. So let's say on the final, you got a perfect score on all the topics that were on test 1, even though a couple months prior you bombed test 1. If you can show me on the final that, yeah, now I know the topics, that's good enough for me. I'm going to be like, okay, this student knows what they're talking about. They're clearly an A student now. I'm not going to punish them because they were a C or a D student 2 months ago. Right now, I am looking at an A student, and that's how I kind of see it, look at it, right? So you do have time to make up for anything in theory. Now, I don't want that to cause anyone to be overly optimistic or to slack off more. Oh, Jhevon will forgive me. That's not what I said. What I said is I'll forgive you if you improve. And if you did really bad, it will likely take a lot of work for you to improve. And of course, with classes being the way they are, that might actually be even harder. But who knows, it might be even easier. Maybe some of you, with the extra time, you don't have to waste time traveling and going to classes and going to all your commitments. Maybe you might even have extra time to actually pull something off, so who knows. So in general, I would say don't freak out about your grade just yet. It'll be a while before it's all said and done, and I would actually just keep trying to improve. And I don't know, how much time has it been? Wow, okay, that took a lot more time. I don't know if I'll actually get to the other topic, but let's actually just go through 2 more related rates examples. Those are all the questions. Thank you for the questions, by the way. Keep them coming. Most people actually submitted questions the way I like, either by putting them down in the comment section of the video or by emailing me through Jupiter Grades. A couple people actually emailed me through my regular Fordham email, and I caught them, which is fine, but I'd rather you not do that because, as you can imagine, in the wake of this whole thing, I'm getting tons of emails at my college address, not only from students, but from the administration talking about, oh, how are we going to change things? And we're still not sure how we're going to deal with testing in the long-distance learning environment, because switching to online testing in a traditionally non-online class is not really doable in the strictest sense. So, you know, there are lots of messages going back and forth in my college email, and unfortunately, at this point in time, it's going to be easy for me to miss an email that if someone is asking a question and it's buried in there. So I'd rather you just email me through Jupiter Grades specifically when you want to ask me a question about a video that I posted, or actually post a comment in the video itself if you don't mind identifying yourself some way. Okay, so that being said, let's actually continue with these guys here. I think from the handout, which again I'll post a link in the comment section, I will go through problem 4 and problem 10. And the problems that I go over, more than likely in an exam, I'll ask you a problem type of this one. The others are still important for you to go through to make sure you're getting the concepts, to make sure that you know the steps to go through. But yeah, I'm going to do these 2 more, and I don't know, hopefully there's some time left over to talk about the other topic. At least I'm definitely not going to finish the next topic, but hopefully I can have enough time to actually just introduce the next topic. So let's actually do problem 4. Like I said, as you can see, it's always the same 6 steps, so I can actually use this as like a template to solve all the problems. So once you learn these 6 steps, you learn the template, it's going to be easy for you. Okay, let's jump into it. As I said, I highly recommend you pause the video, pause it, try problem 4 on the handout, then start the video again. I'm going to run through it, and then you should just let me know if you understood or if you got something different or you did something a different way and you might want to ask me about that. You can ask me about that. Pause the video, pause it right now. Do it. Okay. All right, let's actually go through problem 4. So step 1 is to read. The volume of a sphere is increasing at a rate of 5 cubic feet per second. How fast is the radius increasing when the radius is 2 feet in length? The volume of a sphere of radius r is given by this formula. So here's something that you'll notice. They gave us the formula. Now, this was given in the problem. What does it mean when a formula is given in the problem? Well, it means not necessary, usually. Now, in my other calculus class, there were situations where the given formula wasn't good enough. They actually needed to tweak things a little bit more, and so they had to draw a picture to kind of figure things out. But in an applied calculus class, I'm not going to give a problem of that level of difficulty. Usually, if it's in a situation where I gave you the formula, you're not going to need a diagram. Because remember what the diagram was about. The diagram was really just to give us an idea of what formula we'd have to set up. Last time the diagram was a right triangle where the labeling were on the edges, and so the idea we got for the equation in step 4 was Pythagoras' theorem. Here, if we're given the equation, we don't need to come up with an equation, so we don't need to really understand the picture. So here, I would actually skip this step. So we still think in this order, but I would skip over step 2, and go straight to step 3 because I was given the equation that I want to use here. So there's no need to actually figure out what that is. Yeah, so let's continue. The volume of the sphere is increasing at a rate of 5 cubic feet per second. So what do we know? The volume, dV dt, is increasing, means it's a plus, at 5 cubic feet per second. And here's one of the things that I mentioned just earlier about where the units might be important. The fact that they said cubic feet, even if they didn't mention volume here, you would know that this 5 is referring to the rate of change of volume because it's cubic feet per second. So it's a cubic unit of length divided by time, that's the rate of change of volume. So the problem does say it's how fast the volume is changing, but even if it didn't specifically mention volume, you should recognize that that's a volume. How fast is its radius increasing? So what do we want? dr dt. When do we want it? Now? Well, no. We want it when r equals 2. Right, and at this point we can throw the question away because we have everything filled out here that we'd actually need. So what we're going to do is we're going to differentiate implicitly with respect to time. The derivative of v is dv dt, and the derivative of this is going to be 4 pi r squared dr dt. That's because the derivative of r cubed is 3r squared, the 3's would cancel, and then I have to multiply by dr dt because that's not t. And so we have that. Now, ultimately notice what we want here. We actually want dr dt. This is the guy that we want over here. So I could solve for it from here. Say dr dt is going to be equal to dv dt divided by 4 pi r squared. And so step 6, plug in. dr dt is going to be equal to dv dt, we know is 5, 4 pi r squared, r we know is 2, so that's 5/16 pi. Now, like I said, it's okay if you leave off the units, I don't care. But if you want to put them on, it would in this case be feet per second. Get out the paper to make sure. Yes, it's feet per second. So radius is a length, so it's feet per second. And that's that problem. So hopefully you tried that and hopefully you got that answer. I'll give you 3 seconds here to pause the video and copy that down. 3, 2, 1, and we're back. Okay, so hopefully that made sense. If something didn't make sense, of course you can ask me that question in the next one. But that was problem 4. Another related rates problem, just another application of the 6 steps. Okay, let's actually jump into another problem. The other problem that I wanted to do was problem 10. Okay, so read step 1. Superman is cruising at 390 feet per second at an altitude of 5,000 feet. He flies directly over Jhevon's house. Assuming Superman maintains altitude and speed, how fast is the distance from the house to Superman changing at the time when Superman is 13,000 feet from the house? Okay, so you've hopefully read that with me. Pause the video, try it, pause it right now. No. Okay, good. Hopefully you tried it. Or maybe you're too iffy to go through the entire problem without knowing if you're right. So okay, we can also do it in pieces. Try to come up with the right diagram here. And so you can pause it, try to at least figure out the picture. And then, okay, you can see if you got the right picture here. So here's how I would think of this. So we have the ground. Let's say here is Jhevon's house. Superman is flying over this, right? So here is Superman. Dun, 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 dun. Dun, 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 dun. Wait, that's not. This is red cape. Right. Now, we know one. He's moving at 390 feet per second. So this is moving at 390 feet per second. The altitude is 5,000 feet. So this height here is 5,000. And we want to know how fast is the distance from the house to Superman changing. So the distance from my house to Superman is going to be this distance here. So we have that situation. So, in other words, we have another right triangle here. It's just as a weird orientation. So we pretty much have that. Now I'm going to make the labeling here. This is 5,000. I'm labeling that because we're assuming Superman is maintaining altitude. Now, of course, this is the point of my house, and this is actually increasing, so I'm going to label that with something. Call that A. This is the distance between my house and Superman. Call that B. Notice that as Superman is flying away, both A and B are increasing. So not only do I expect the rates mentioned to be positive, but I also expect the answer to the question to be a positive rate as well. So all that goes into me thinking about my diagram. I'm going to plug in that constant because it's constant altitude. So that is the diagram. Okay, so if you got that diagram or something similar to it, something equivalent to it, some students might have the triangle oriented a different way like this. In that case, you'd have to think of the Superman flying as this length as decreasing, it'll actually change how the answer would look, actually. But because the problem said he already flew over the house, which means he's leaving it, not approaching it, I think this is a more intuitive way to fill out the diagram. Okay, so that's the diagram. If you didn't get the diagram, okay, hopefully you learned your lesson from it. Pause the video. Assuming that's the diagram, fill out everything else. Okay, 3, 2, 1. Okay, so let's go in. We know that he's cruising at 390 feet per second. That tells me that dA dt is positive 390. I call it positive 390 because I'm assuming Superman is flying this way, so A is getting larger, it's increasing. How fast is this Superman to the house changing? So I want dB dt when Superman is 13,000 feet from the house. So this length here is 13,000. Okay, so that's how that step would be filled out. Pause the video. I'll give you 3 seconds to come up with the, pause it and come with the equation. 3, 2, 1. Okay, so the equation that would apply here is again Pythagoras' theorem. The difference is here though, b is the hypotenuse, so it's actually a squared plus 5,000 squared equals b squared. That's the equation, Pythagoras' theorem. Now, that leads you to step 5. We're going to implicitly differentiate with respect to t. The derivative of a squared is 2a dA dt. The derivative of 5,000 squared is, that's right, it's 0. Derivative of b squared is 2b dB dt. Now what I care about is dB dt. I can solve for it here. First of all, divide both sides by 2, then divide both sides by b. So this is a dA dt over b. So now I'm going to plug this in. dB dt equals a. I don't know what a is. A, we're going to plug in here. dA dt, I know that that's 390. Over b, I know that's 13,000. Now, how do I find a? Now remember, whenever there's information, I want to plug in a constant in this step, but I don't know what the value is. I always go back to step 4. Now in step 4, we know that if b is 13,000, that's the equation. Now you wouldn't want to have to square 13,000, however, you should know that a is here actually 12,000. Because there is such a thing as the 5, 12, 13 triangle. That's another one like the 3, 4, 5 triangle. Those numbers show up very often. Because 13 squared is equal to 5 squared plus 12 squared. Because that's 169, this is 25, this is 144. So these are numbers that occur together. Now of course, it's proportional, so if I multiply each side by 1,000, that must be the case, that 13,000, 5,000, and 12,000 should all show up together, and so that gives me the a value right away. Of course, you could calculate what this guy is and actually take the square roots and do the subtraction, but that's actually not as efficient as just knowing about a 5, 12, 13 triangle. 3, 4, 5 triangle and 5, 12, 13 triangle I think are pretty much the only ones I'll ask you about. So I come back here and plug that in. So that's 12,000 here. Now of course we can start to get to canceling. So the thousands cancel, and 13 goes into 39 3 times, so that's 30. And so that's just 12 times 30, which is 360. And that's your answer, positive 360. And in fact, you could know that this is feet per second, but I don't care about the units at this point, as I mentioned. Okay, how much time do we have? But yeah, that's the answer there. Hopefully that went fine, but let me know if you have any questions next time. Okay. So in the next few minutes, I just want to start introducing another topic. Actually, no. Ordinarily, I'll just do it, and if I go a few minutes over time, I'd be like, it's fine. But I actually went a little bit over time in the last video, so yeah, I'm outrunning my grace period here. So I think that's it. We'll just stop this lecture at nothing but just doing more examples with related rates, and I answered some of your questions, which hopefully that was helpful, and you kind of know how I think about grading and what to. How to improve, and hopefully answering your questions was actually helpful. So, as I mentioned, what testing would look like moving forward is still kind of up in the air. I'm still kind of deciding, and the math department as a whole, we're still all kind of deciding how we're going to want to do that. Of course, I'm going to continue with online homework. That's not going to change, but for now, I think quizzes are suspended. There's no real way to give you a real quiz, as well as, I don't know, for the second exam and the final, I don't know how that's going to look. This might blow over in the next month and a half or so. No way to know for sure, but I'll keep thinking about it in the moment where I think of something that would not only be fair to you guys, but also would maintain the integrity of the class. Not that I don't trust you guys, but it's important for transparency reasons that we test you in such a way that people won't be able to say, oh, well, they could have just cheated and get, you know, we have to be above suspicion, above board, and kind of transparent. And yeah, what that's going to look like, I don't know at this point. But hopefully you should be good with related rates now. Hopefully that answered all your questions. The next thing I'm going to talk about is maximum and minimums, absolute max and mins. Max and min values. I'll talk about something called critical points. I'll talk about absolute maximum and minimums. And the closed interval method, which just tells you how to identify absolute value, absolute maximum and minimums. So that will cover, I think that's a good deal of things to cover for the next lecture. So if you've taken calculus before, you can review that a little bit before I start, or just keep working on the stuff I already gave you. If I didn't post a homework for related rates, I guess I will do that. Have you guys work on that in the meantime. What I will do is, technically the week coming in, hopefully I'm right about this, would have been your guys' spring break anyway. So we should have had this COVID thing not happen, 3 lectures this week. This is actually the second lecture. What I'm going to do is post another lecture tomorrow, which technically is Saturday. I know you guys wouldn't have class normally, but post a lecture tomorrow. That would round out our 3 lectures for the week. This will probably be what I'll talk about, and we'll do local maximums and minimums, I guess, when school starts again. So a couple days before spring break ends, I'll probably record a lecture on the next topic, and you guys can ask me questions about that leading up into that week. In the meantime, keep sending me questions. Whatever concerns you have, you can let me know. As I said, I prefer if you email me through Jupiter Grades, or if you have a specific question, tell me the timestamp for the question. Oh, in this lecture at this time you said this. I don't understand that. That would be great. or drop it down in the comment section. In either case, you need to timestamp it so I know where to address or what to look at. What did I say that might have confused you? We'll stop there. Be safe, and I'll see you in the next COVID lecture.